Just like to reach out and greet you from sunny southern Minnesota. And yes, it is Owatonna, and that is an Indian name, as you could imagine. And Owatonna, what that means in the original native language, is the land of the great desiccant manufacturer. Just kidding. So welcome to Psychrometrics 101-201, the science of moisture and air. Well, psychrometrics or psychometry, what is it? It is the field of engineering concerned with the determination of physical and thermodynamic properties of the gas-vapor mixture, that one we all know and love, that we breathe in and out all day long. So this is a psychrometric chart, and I just want to do a really high-level overview of this chart. Let's look at the borders. On the borders, on the very bottom, in a straight horizontal line, we're going to look at dry bulb temperatures. This top curved line represents air that is at 100% saturation or 100% relative humidity. Across the right side are going to be all the absolute measurements of moisture. And so as I would start at this lower part of the chart and move up, what's happening is I'm adding moisture. If I start here to the left and move to the right, I'm getting to a warmer temperature. So we'll go through this in detail, but that's just a real quick bird's eye view of the psychrometric chart. Let's move on and talk about why we control moisture. First of all, in our current situation, the Stirling chart becomes pretty interesting. This has to do with the relative humidity in a space, starting at 0, going up to 100%, and how much viruses or bacteria or whatever might grow. And so today, we're all tuned in on viruses. So you can see that if we were to hold a room at 50% relative humidity, or between 50 and 60% relative humidity, that it is the optimum zone provides the least hospitable atmosphere for viruses to grow. So we might today decide to hold a room between 50 and 60% relative humidity. And when you're talking about our normal spaces, 70 degrees, 50% RH, not a difficult thing to do. But what happens if you're a food processing facility, and we've heard about a number of those? It's a 45 degree or cooler processing room. How can we get there? In our example, a lot of detail here in the slides, but our target is going to be to increase production, and I'll get into this a little more detail. Increased production, have a 0 tolerance to condensation, and try to get that relative humidity down to something lower than saturation. Here's the detail on the space, outside air, how many people. These are all the things we need to collect as data so that we can do our load calculation. Our design criteria is to stay below dew point. Any one of these moisture-related applications, we would submit to you that it's very important to understand and separate the moisture load out completely and what it takes to remove it. You might be using some software right now that does a very good job of people moisture, outside air moisture, some of those things. But as you get into tighter and tighter conditions, other factors start to show up. So let's take a look at it. In the food process application, they are processing for some period of time. And in our example, we're going to try to get to 10 hours of production. And then it takes them approximately 1 hour to wash down the room or clean up. And then they want us to recover the room and get it back into production in 1 hour. So during a production mode, what does it look like? Well, we're going to be supplying air at 37 degrees so that we're going to discharge a offset temperature, a lower temperature. So as it goes through the room and the room warms up that air, we're going to return at our control condition of 45 degrees. Minimal amount of outside air, whatever that needs to be, and we're going to positively pressurize that room just a little bit so that the air moves back toward the dirtier parts of the food process. So that's the production mode. But then there's cleanup, and hopefully you can see a little slide in the center here. What that's showing is these folks are spraying 140, 160 degree water around with some chemicals in it, washing everything. And as you hit these 45 degree surfaces, it just absolutely creates a fog. Everything's dripping, everything's wet. The space could warm up to as much as 70 to 80 degrees during that time. We're generally at 100% outside air at that point and 100% exhaust during the cleanup mode. After cleanup, then we move to recovery. Depending on the condition of the outside air or condition of the space would determine whether we're using outside air or space. But in this particular case, we're saying no outside air. It's 100% return starting at 70 degrees. And now we've got to pull that room down, and pull it down, they've said, within 1 hour. So what does that load look like? After we pull it down, it's back to that process condition or that work condition. What are our load calculation considerations? Where does moisture come from? Permeation. That is the moisture that can come right through the wall if the wall is permeable. In our example today, the walls are not permeable. They have a vinyl interior. The product. Is there something outside of the room that's coming into the room that's going to be giving up moisture? Personnel. How many people are in the room giving up moisture? Is there any gas combustion like an LP forklift? Evaporation. Is there any moisture that's on surfaces that are going to evaporate? Infiltration. CFM coming into the room, whether it's cracks, doors, openings, and not only CFM, but we also have to remember the vapor pressure differential that's going to try to push that moisture into the room even though the room might be positively pressurized or the doors are closed. So infiltration. And then ventilation, the outside air. Those are the major components of moisture in air. The one that we're talking about today that's going to be very prominent is that room that is now totally saturated. Every surface is wet. And so we're going to use this formula to determine how much evaporation we're going to get from those wet surfaces. Here are the values that we're going to use to do that. We've done this work offline, so I'm not going to go through that in detail. What it works out to be is during production, there's 45 tons of sensible load in the space and only 18.5 tons of latent. So our total load is 63.5, and if I divide the sensible to the total, we get a heat ratio of 0.71. And that would look something like this on our psychrometric chart. There's our control condition. Here's the slope of the line during production. Let's do the same thing now, but during recovery. Look at the latent load. It's gone all the way up to 132 tons. So 177 total. The sensible to the total way down here at 0.25. Now look at our line. The sensible to total heat ratio line moved quite a bit toward vertical. So the question becomes, how can we get on that line so that we can dry up that room in the 1 hour that we've been given? How do we get to some place on that line? This is where we would look at the system and ask ourselves the question, can we provide air at a low enough dew point to offset that moisture load? And we'll look at temperature as well. Here's the formula that you could use to do that. We know the amount of moisture. We're going to measure that in grains. 4.5 is the constant times the change in grains. What kind of a change in grains can we get? And then we can solve for CFM. In this case, again, it was 1,508 pounds, 7,000 grains per pound. That gives us our total grains. How much grain depression is possible? We're answering the question, can we provide air at a low enough dew point to offset this moisture load? How much grain depression is possible? Our control level being 42 grains, that's what we're trying to get to. That's the return air coming into the system. We mix it with the outside air so we can get to 46 grains. And if we make a selection, and we can find out that we can get down to about a 12 grain outlet fairly easily, so that gives us a 30 grain depression. So our solution, here's our load at the top, divided by 4.5 divided by our 30 grain change, tells us we would need 78,000 CFM to be able to dry up that room in 1 hour. The benefits of using desiccant drying for this sort of application, one is that we can go to blow-through cooling as compared to draw-through. That gives us the ability to put the fan heat in front of the cooling coil. The cooling coil is going to see sensible load only, and that allows for a much more efficient system. You can use, get to a lower leaving air temperature, and you're not going to have saturated air. So if the system has final filters, those filters will not become wetted, as the air would have a pressure drop across the filter and therefore leave moisture in the filter if it were 100% saturated. So no more saturated air. You can have dry filters downstream. This is what it looks like on the psychrometric chart. We're starting at the mixed air condition. We're going through that desiccant dehumidification process, adding a little bit of fan heat coming out sensibly to the right, and then post-cooling down to, in this case, that 35 degree condition. That's what we can get to with the coil. Gives us a full 10 degrees of differential between the coil and our discharge condition. And we can now do that tonnage during production with less CFM. So we can reduce our CFM potentially. There's also optimization of the system, especially in food processing. The question has to be asked, when is it dry or dry enough? And maybe there's two answers to that. There's one for the FDA, which says no condensation, I can't have water dripping on my food, but the floor can still be wet. Or the one today, going back to the Stirling chart, should we try to control that space to 60% RH? With this equipment that we've selected today, you can really do both. It's a matter of how much energy you want to burn, but the system is there to hold the space at that condition. We're going to keep moving along. Our next application is the hospital surgical suite. This one is different in that the air change requirements are really defined for us. Earlier we were saying how much air does it take at the condition that we can achieve to do the load. Here we've been told that we need 20 air changes. Now ASHI is continuing to evaluate the air change requirements. Maybe they'll go down, maybe they go up, but there's some work being done to determine, is the 20 correct? It was 24 here a few years ago. Our example today, we've gone ahead and done a load already. We've talked through these a little bit. We do have webinars available on load calculations. If you want to sit through in infinite boring detail about where room load comes from, we can do that. But there's the part that happens to the room and then the ventilation. And most of the time, rule of thumb, the ventilation, the outside air is going to be the biggest part of the load. Not always, but most of the time. And here you can see it is as well at about 88% of the load. So this part up here, this is what's happening in the room. That's our room load. On the left-hand side, you'll see the total load, the 88% outside air shown here. This little pie in the middle is the room load. It's made up of the personnel, the moisture that's permeating through the walls, the door being open and closed, the cracks that are around the room, allowing moisture to get into that space. So we again are going to discharge the air condition that we need to allow for the room gain. Here's the load, total load. Here is the room load. So you can see in this application that the room load is not a very big piece of it. This is the control condition that we're trying to get to, 62 degrees, 50% relative humidity, 41 grains. That's what we're going to try to hold the room to. If we have our outside air condition, our 62 degrees, 41 grains, 50% RH, It's 20% outside air. That is our mixed air condition. Again, what supply condition do we need to get to that's discharged at an offset for this room gain? Here's the formula. Here's our moisture. 4.5 our constant. Our CFM has been determined for us at 20 air changes. This example is a 25 foot by 25 foot by 12 foot operating room. That tells us that we have to discharge at 3 grains below the room of 41 to offset that gain. Sensible heat, here's the formula to get to that. We've done our total heat and latent. This is the sensible to total heat ratio line. How do we get there? Can I get there with cool reheat? Is it possible? We start at our mixed air condition. We cool to a point of saturation so that when we reheat, we can come onto that sensible to total heat ratio line. So can we get there? Can you get to a 40-degree leaving air temperature? Well, not with 45-degree chill water. Can you do it with 38-degree chill water? Maybe. But it comes at a pretty high cost. And then there's the cost of reheat. So we're using our psychrometric chart to determine how do we get from point A to point B. While we're talking about cool reheat systems, let's just kind of follow this through a little bit. This is showing a elevation view of an equipment room coming down the outside air shaft, our outside air coming into the air handler, the return air coming this way. We're blending that air. We're going to cool it down basically to the point of saturation to get that moisture to come out. And then the fan, maybe some final filters, and we're going to then discharge that very moist or potentially saturated air into this ductwork until some point at which it's going to be reheated. At this point, I'm going to ask you, why was it that we're trying to hold in that room below 60% relative humidity? That's because bad things grow above 60% relative humidity in the room. If you were to take that same surgeon up and have them look inside this air handler and look at this 95, 96, whatever percent relative humidity airstream until it gets reheated, what would they see? What would they swab? So we would submit that if you're going to hold the room to that condition, 60% or below, that we really should be holding any air that's in this duct below that condition as well. So why are we using cool reheat every day? It's because we understand it, and on a design day, it does show the lowest cost of operation. Why not use cool reheat? Well, on cool, wet days, or days that are not design days, in order to get 1 grain of moisture out, you still have to bring that whole airstream down to the point of saturation to get a small amount of moisture out. And if we look at how many design days there are versus the other days, you'll see that there are much more time is spent at other conditions. And again, saturated air can grow things where you can't see or get to them to clean them. Our normal solution for hospital operating suites is to use an active dedicated outdoor air system and provide that air to your sensible primary air handling system. This could be done both from a retrofit as a new application. So you've got a cool system there now, cooling and reheat. But if we add this active desiccant to it, so there's a cool reheat, we add this desiccant dehumidification system to it, just to the outside air. We take the outside air, the 4 air changes, and pre-cool it to get the most of the moisture off, or some kind of a first stage of device. Then go through the active desiccant. We provide air that is, if you will, over-dried, so that when it mixes with the return air, now we're going through the rest of the system. This cooling coil that's in the system now is sensible only. And we're discharging air that's going through here that's below your 60% relative humidity. That includes then the ductwork. So now the ductwork is going to be dry as well. This is what it looks like on a psychrometric chart. We're going to take the 4 air changes of outside air. I'm showing a pre-cooling coil. Now we can get by with just your normal 45-degree chill water or 45-degree DX system, whatever pre-cooling we'd want to do. It can even be heat recovery, although that is becoming less and less of an option in hospital operating rooms or anything like that. So most of the time it's going to be some sort of coil. We go through the desiccant dehumidification. Relatively long line again. Why? Because that's only 4 air changes. We're going to then provide that air to the outside air connection on the air handler. That's this condition. Here's our return air, relatively short line, so there's a lot of air at that condition, 16 air changes, a little bit of fan heat, and now we're going to post-cool it to the condition. So reheat's not required. Dedicated outside air to the sensible air handler. The cooling coil can run dry, can now be a 3-row coil or something like that instead of an 8-row or a 10-row. The air pressure drop then comes down, the horsepower can come down. So several advantages to just dealing with that outside air and over drying it. Why do we use it? We can get to, we can maintain, and we can even pull down to any desired conditions. And it is going to have the lowest energy costs because you now have 2 tools to work this sensible and latent moisture load. You have the cooling coil that's going to work on the temperature, and you have the desiccant that's going to work on the moisture. In a cool reheat system, it's the cooling coil that's going to try to do both, and that's why you have to have the reheat. So it's going to have the lowest energy cost over the course of a year by disconnecting the moisture from the temperature, and it's going to be easier to control. Let's look at some energy comparisons of the cool reheat versus the active DOAS. Pretty simple to see. This is for an application that was here in Minneapolis or somewhere in this neck of the woods. Cool reheat. This is the supply fan at the top, the fan in the air handler. This is the heating, the reheat, and then the cooling. Compare that to the active DOAS system. So the cooling now becomes much, much less. About a third. The supply fan, in addition to the 1 fan for the air handler, we now have fans in the desiccant system, so that goes up just a bit. And then we have the reactivation heat. But when you look at a whole year, we're going to save about half of the energy. So in a comparison of cool reheat versus active desiccant dehumidification for the hospital surgical suite. Remember that new application that we have out there for your phone. Search for Dry Tools and it'll be right there. Thank you for joining our webinar today. Looking forward to seeing you in a future webinar or in person. This is Dr. Dry from CDI. We are your manufacturer for desiccant-based dehumidification systems, along with air handlers for critical process environments like food processing. Thanks for joining us today. Please enjoy the day. Bye for now.